The Cramer theorem provides one of the most well-known results in linear algebra, and according to my experience, it's so very appreciated by students since it gives a formula for solving a linear system. That is, it provides a concrete path to escape a specific situation. Let me show you how this theorem can be stated. Consider a linear system described by the coefficient matrix A with right-hand side term B. That is, the system can be written in matrix form as A times X equal B, the star denoting the product among matrices. Assume A is a square matrix, then A belongs to n times n, the collection of matrices with n rows, n columns. We will say that the system is a squared system in order to say that it is run by a squared coefficient matrix. And furthermore, let the matrix A be non-singular, that is, its determinant will be different from zero. Of course, we will often describe this system as a non-singular system. Then, the solution of the system is unique, and it can be found through the formula X equal the inverse matrix of A minus 1, times the right-hand side term B. Now, let's proceed with the proof. First of all, we want to verify that this formula truly holds. What does this mean to have a solution? A solution transforms the equation in an identity. Hence, it solves the system. And we want to prove that the vector x dot solves the system. That is, when I plug it into the system, it is transforming it into an identity between vectors. Thus, the thing that must be done is to substitute x dot into the expression of the system and see if what we get is or not identically equal to the right-hand side vector B. Now, remark that the product among matrices is not commutative, but it is associative. Hence, I can move brackets and, for instance, proceed multiplying A times A minus 1 first, and then multiplying by B. By definition of inverse matrix, the product of any matrix times its inverse provides the identity matrix. Then I deduce I times B. The multiplication by the unit matrix leaves the vector B unchanged, and we deduce that effectively B is equal to B. We have obtained an identity and finally conclude that x dot is indeed a solution. Now look, the thesis of this theorem is made by two parts. We still have to prove the uniqueness of the solution. The solution x dot is the only solution of the system. Usually, proofs about uniqueness are made by contradiction. You suppose that there are two quantities with the same property, and I show that these quantities actually coincide. Now, let's assume that u dot and v dot are two vectors in Rn that can change the system into an identity. That is, if I pre-multiply the vector u dot times A, I obtain identically the vector v. And if I use v dot and I pre-multiply it by A, I will identically as well obtain the vector b. Let's suppose that these two solutions, u dot and v dot, are different. I can remove the second row from the first row side by side. At the left-hand side, factorizing A, I obtain A times u dot minus v dot. And at the right-hand side, b minus b is the zero vector, obviously. Now, I remind you that the matrix A is non-singular, hence, there exists its inverse matrix A minus 1. I will now multiply by the inverse of A each side of this identity, the multiplication being from the left. Again, we use the associativity property of the product and multiply first A minus 1 times A, and then we will multiply by the difference of the two vectors u dot and v dot. At the left-hand side, we get the identity matrix times u dot minus v dot, and at the right-hand side, any matrix multiplied by the zero vector gives the zero vector. And then we conclude u dot minus v dot is the zero vector, that is, u dot and v dot coincide. Hence, we have reached a contradiction. The two vectors in Rn that were supposed to be solutions of the system actually are the same solution. Every component of the first vector is equal to the corresponding component of the second vector. We have just one solution of the system. And this concludes the proof of the Cramer theorem.